engine running.
Absolute genius.
Get this.
Welcome.
This is the show where we bring you
Science.
What that essentially means is
discoveries,
Advances.
Questions. Research.
technology. Unbelievable.
Without further ado,
This is The Naked Scientists. Hello, welcome to the Naked Scientists podcast. This is the show that brings you the biggest breakthroughs and talks to the major movers and shakers in the worlds of science, technology and medicine. I'm Chris Smith, and today, to celebrate 10 years since they were first detected, we're examining gravitational waves. What are they, and how do we find them? Literally a decade ago, on the 14th of September 2015, scientists heard the universe in a brand new way when they detected gravitational waves for the very first time. Fast forward 10 years, and the global network of detectors, LIGO, Virgo and CAGRA, have now published more than 200 instances of gravitational ripples in space-time, the fabric of space. Each one has not only confirmed the existence of gravitational waves, but nudged our understanding of gravity in surprising directions. And that's what we're going to explore this week. The physics of gravitational waves, how the detectors work to find them, and why, in another 10 years' time, gravitational wave detection is destined to make a massive leap forward. But, backing up slightly, we first need to return to the past, because the roots of this story stretch back centuries to a young scholar wandering the courtyards of 17th century Cambridge. His name? Isaac Newton. Nicholas Bell, librarian at Trinity College, where Newton studied, and home to many of his books, notes, and even his armchair, has been telling me all about him.
In front of us, I have a copy of the first edition of the Principia Mathematica by Isaac Newton, printed in 1687. This copy, it's actually one of several in this library, and it's quite heavily annotated by Isaac Newton himself, because after he'd printed it, he then spent a lot of time revising it for a second edition. And you can see annotations on almost every page.
And this is all in Latin. Was that standard for these sorts of texts?
It is quite standard to be in Latin. I think it's very interesting, actually. His second famous book, The Optics, was printed in English first and then later in a Latin translation, whereas the Principia Mathematica was first printed in Latin and then in English. He really had a continental readership in mind. He wanted people to be able to read this in every country, and therefore Latin was a more appropriate language to use than English.
How does Newton get interested in gravity? Is the apple tree story just apocryphal? It's just a good story, or is there any kernel of truth in that?
There should be a kernel of truth. The precise details aren't totally clear, but we know that in the year 1665, there was a risk of the plague coming to Cambridge. In fact, to protect against it, the members of the college were asked to go home if they possibly could. Newton returned to his mother's farm in Woolsthorpe Manor, just off the A1 today, and there is still an apple tree outside that house, which is the tree that was alive in Newton's time, and about which he writes about watching an apple fall. It could be that he's applying it post facto, as it were. He realizes this and then uses the apple as a way of demonstrating it. But that's what he tells us anyway, that was how it came into his head.
I'm pretty awe-inspired. I'm a bit starstruck, to be perfectly honest, sitting in front of this book and what this did to the world. So when he then comes up with this concept of gravity, presumably people had never asked the question beforehand until he writes this.
It depends what the question is, I suppose. I think people had wondered, and different ideas had been expressed in different ways by many people. I mean, even since medieval times, the question of why things fall when you drop them. But this systematic exposition was so thorough and included so much mathematical proof of all of his theories. It raised the discussion to a completely different level because it's no longer based on conjecture. It's all based on fact and on observation.
And what happened to Newton afterwards? Once he published this tome, how did his life change? Or was this just another day at the office for him?
For one thing, he became very defensive about his theories because he received quite a bit of criticism. some of it took several years to materialize. One of the main criticisms that came for this book was that although he explains how the whole of the cosmos works, he explains the movement of the planets relative to the sun and of the moon and the orbits and so on, he doesn't come up with a grand origin theory. He doesn't say there was a Big Bang. He doesn't say God started the planets moving. And some people were annoyed that they took this absence of a theological context as being too provocative, when in fact that wasn't part of what he wanted to do in the first place. It was purely a mathematical work to demonstrate the facts.
Does he acknowledge anywhere that I can explain why we're seeing what we're seeing, but I can't explain why it happens in the first place? Does he actually acknowledge that?
In the first edition, he didn't. And he then had long discussions, especially, in fact, with Richard Bentley, who was master of Trinity. There were some printing errors in this book, and Newton knew that he wanted to print a second edition. Once Bentley knew about this, he wanted to make sure that this new edition would have a new introduction which placed all of these ideas in their proper theological context, which is to say, he wanted to have a preface saying, "In the beginning God made the world," and then the planets started moving in the following way.
What did Newton make of that?
Newton just refused adamantly. I can show you some of the letters, in fact.
This is 1692, this says here.
This is 5 years after the publication, and Newton proposes that the motions which the planets now have could not spring from any natural cause alone, but were impressed by an intelligent agent. Now, that's an amazing phrase. He's proposing the possibility that an intelligent agent enabled the planets to start to move. But he doesn't assert it. And then he says, the sun, he decides, is a man. The sun may, by heating those planets most which are nearest to him, cause them to be better concocted and more condensed by concoction. But when I consider that our earth is much more heated in its bowels below the upper crust, by subterraneous fermentations of mineral bodies, than by the sun, I see not why the interior parts of Jupiter and Saturn might not be as much heated, concocted, and coagulated by those fermentations as our Earth is, and therefore this various density should have some other cause than the various distances of the planets from the sun. It's a wonderfully rich sentence in so many ways.
Very insightful. When you think he was writing that hundreds of years ago, no one had been off this planet, let alone probed what was inside other ones. And he's got really quite a strong insight into what must be going on, hasn't he?
And he's almost admitting that he wants to believe that it is the heat of the sun that is powering the solar system. But he can't reconcile that with the fact that he knows that the centre of the Earth is hotter than the outside of the Earth.
But it's showing a questioning mind, isn't it? It's showing I want to see evidence-based proof for what I see around me.
Absolutely, yes. That seems to be his main wish in that letter.
And I have to say, I was incredibly struck that Isaac Newton had the most amazingly neat handwriting, and all in perfectly straight rows. What a fascinating morning that was. Thanks very much to Nicholas Bell at Trinity College's Wren Library. So, Newton had come up with a way to calculate the observed effects of gravity, although he couldn't explain what it actually is or how it works. That required the huge intellect and insights 300 years later of Albert Einstein, who reimagined gravity entirely. It was not, as Newton had viewed it, a force pulling on objects, but instead the bending and warping of space and time itself. And from this bold new picture came predictions that seemed almost impossible. The existence of black holes, and the subject of our analysis this week, gravitational waves. So what are they, and how do they work? Well, here's Ben Alanak. He's Professor of Theoretical Physics at Cambridge University.
Well, Newton thought of time and space much like we do, which is, they're kind of rulers, right? And that you can't affect them. Time just carries on and, it's really a marker between different events. And the same with space. It's just like a ruling and, you can't change space. It's just there or it's not. And Einstein already knew in 1915 that space-time is actually one thing. You can't discuss them separately, and that it differs for different observers. And in particular, by then he knew if you're traveling fast compared to someone else, you'd measure time differently and you'd measure space differently as well.
People often say Newton's calculations work really well under certain circumstances, but they break down at the extremes. What do they mean by that?
Yeah, that's right. So Newton's laws work for planetary motion very, very accurately. But if you get close to the speed of light, which is 300 million meters per second, so it's an incredibly quick speed, then they break down, and that's what Einstein already knew at that point. But later on, when he developed the theory of general relativity, he also realized that when you get extremely massive bodies, they also break down. Newton's laws also break down.
You're saying he already knew that. How did he know that?
Well, he'd already developed the theory of special relativity, there were various experiments showing that, for example, cosmic muons decay with longer times when they're going very quickly. And in fact, lots of measurements showing that time travels slowly when objects go fast. But then also, when you go very fast, you actually mix up what you mean by space and time compared to other observers. So that's why he realized that space-time is a physical object, and you can't discuss one without discussing the other in general.
People talk about envisaging the fabric of space almost like the surface of a trampoline, because it works in a certain number of dimensions, doesn't it? Because you can bend it, warp it, a bit like a massive object, like a star would, and then things roll into the dip, and that's like gravity. I mean, is that a reasonable way of envisaging space-time?
Yes, absolutely. So if you've got, you just reduce the number of space dimensions by one. So pretend we were only in a two-dimensional space universe. Then you can absolutely imagine some rubber sheet. You put a big heavy ball in the middle, and it'll curve it and make a dip around it. And then a light wave might be some light marble that you roll around this ripple, and it'll tend to go around the sun because it'll go around the big dip. And that is actually a very good physical analogy for what's happening. And Einstein's equations, the equations of general relativity, are a very mathematical theory that precisely describe what's happening with that in 3+1 dimensions, how that generalizes.
Taking that forward then, if we've got gravitational waves, would that be like me hanging onto one side of your trampoline and basically giving it a stretch and pulling a bit of it towards me and letting it go so I get a compression wave, a bit like a sound wave? Or would it be like me shaking the trampoline from side to side? What are gravitational waves in that respect?
So this is going to be important for the future. So let's take the example where you've got your rubber sheet and you've got two very heavy marbles in the middle that are going around each other in circles. And what they'll tend to do is they'll make ripples in the rest of the trampoline that travel out along the trampoline. And so these waves in the very fabric of space-time is precisely what gravitational waves are.
Does that mean then that these waves can have different wave lengths? In the same way as if I go to the beach and I could record the distance between the peaks of waves arriving at the seashore that I could surf on, that I get some waves that come very close together, short wavelength, other waves that are spread out a long wavelength. Do gravitational waves do the same thing?
Absolutely. They travel at the speed of light, but their frequencies differ depending on what produced them. You might have two of these big marbles going around really, really quickly, and then the frequency is going to be high and the wavelength will be small, the wavelength of the ripples. But if you have two enormous, great big building wrecking balls going around each other, then the wavelength will be much longer. Yeah, absolutely.
And therefore, if you've got bigger objects, you get bigger or different wavelength gravitational waves. But even so, they'll contain information about the thing that made them.
Yeah, absolutely. For example, black holes that they've been seeing, a lot of them, you can see them when they get quite close to each other because they produce stronger gravitational waves of the right frequency. And so you can see them going round each other, or you can detect them going round each other. And then finally, the frequency goes up when they get quite close to each other and then finally fuse presumably into a bigger one. There's what they call a chirp signal, and the intensity goes up. You can even listen to it if you look at chirp on gravitational waves. You search for it on the internet. They've made it into a sound signal. And that's literally to time as well, so it's all very quick.
And you said this intriguing thing that we can actually now both look with optical telescopes and look with gravitational wave detectors at the same patch of sky, see the signals arriving simultaneously. So does that mean we can integrate two different types of astronomy then? You've got gravitational wave observation and visible light, and get information from both, presumably.
You can do it sometimes, not for all of the gravitational wave signals. Sometimes you get a black hole which is coalescing with a neutron star. And in that case, there's the neutron star coalescing with the black hole gives off some visible light. And it also gives off the gravitational waves because they're two heavy bodies. So what happens is the gravitational waves detectors see it first. They have a look through a telescope to see if there's any visible light. And if there is, then immediately a signal automatically goes out to lots of interesting telescopes that point at the right part of the sky and try and find the optical signal. And you can tell all sorts of things that are going on, all sorts of physics of neutron stars. The discovery of where gold was made was confirmed there, and so on.
What do we still want to know about gravitational waves then?
Well, we're in the early days. They've only been going 10 years. They're very useful for astronomy because you can see earlier in the universe. There's this weird thing, right, that when you look further out, you're actually seeing further back in time because the light has taken so much time to reach you. But the thing is, there's only so far you can see. You can see back to after 380,000 years after the Big Bang, because before that, the universe was so hot that the atoms weren't electrically neutral and light didn't propagate through them. So you can see that back to this, what's called the surface of last scattering with ordinary light. If you use neutrinos, which is happening, you can go back to about a second after the Big Bang before it becomes opaque. But gravity travels through all of that. And so, at least in principle, when your detection gets sensitive enough, you can see way back into the first second of the Big Bang. The important timescales are logarithmic. So, the first second is important as the next 10 seconds, which is important as the next 100 seconds, and so on. So a lot of physics happen in that first second of the Big Bang that we'd really like. We've got theories about it, but we really want to test them.
We certainly do. Physicist Ben Alanak there.
The Naked Scientists podcast is produced in association with Spitfire, cost-effective voice, internet and IP engineering services for UK businesses. Find out how Spitfire can empower your company at spitfire.co.uk.
Music in the programme is sponsored by Epidemic Sound, perfect music for audio and video productions.
This is the Naked Scientist podcast with me, Chris Smith, and today we are marking 10 years since the first detection of gravitational waves, and we're finding out why they matter. But how do we actually detect gravitational waves, and why, if Einstein predicted their existence, which he did it take until 2015 for us to first see them? The answer is that people were trying for decades, but it was only relatively recently that our technology reached the point that we could nail it. And when you hear Gabriela Gonzalez, an experimental physicist at Louisiana State University and the Laser Interferometer Gravitational Wave Observatory, LIGO, where all this happens, explain what's involved, you'll understand why. But first, I wanted to know from her, how would I recognise a gravitational wave if one came along and slapped me around the face?
Gravitational waves actually change distances, but they are so small that we wouldn't feel anything. Even the whole Earth wouldn't change much. That's why we have to build these sensitive detectors to be able to hear these gravitational waves.
And how do these detectors that you've built work then?
We use lasers to measure distances. So we measure the distance between two mirrors. We make the light go back and forth using the wavelength of the laser as a ruler. However, measuring distances is very difficult. So something that we use to our advantage is measuring differences in distances. So the laser, we split it in two and we make it go in one way straight, and the other half of the laser goes in a perpendicular direction. So we do have mirrors in each arm of this L-shaped detector, and those lasers go back and forth measuring those distances. And when the lasers come back from each arm, then they meet each other, and at the output, they interfere with each other. That's why we call this an interferometer. That means the two laser signals, if the two distances are exactly the same, they would cancel each other. there would be no light coming out of the detector. So if we see light and if we see the amount of light out of the detector changing in time, getting in brighter and dimmer, that means we have detected a gravitational wave or something else, because there are lots of things that make the mirrors move, not just gravitational waves.
So you have an L-shaped detector and you split a laser beam down each of the arms of the L. So imagine we're putting the beam in at the angle of the L. Why should it work with two beams in that way? Why should the gravitational wave stretch or shrink one bit of the L but not the other to make that work?
Einstein's theory, which is a theory that predicts the existence of these gravitational waves, tell us that distances get longer and shorter, but not the same in all directions. In this L shape, if the distance between the mirrors in one arm gets longer, then in the other arm gets shorter. There's a very fancy name for this, quadrupolar waves, but that's all it means. And that's why measuring the difference between these lengths gives us a signal.
And the light beam, therefore, it started off together. It was the same laser beam that you split, and it's travelled a slightly different distance down one arm than the other. So when they come back together, those beams are now not lining up anymore, which is why you see light, where if they did line up, you would only see darkness.
That's right.
So, to what extent does the gravitational wave change the path of the light, the distance it has to travel, in order to produce the effect that you're seeing then?
It's really, really tiny. In fact, the amplitude of the gravitational wave is measured in the fractional change in distance. That's one of the reasons why we want very long detectors, because our limitation is in the change in distance that we can measure. But even with 4 kilometer detectors that we have, 4 kilometers in each way, the distances that we are measuring are smaller than an atom, smaller than a proton. They are 4 parts in a thousandth of a proton.
Goodness me, a fraction of a
Incredible.
proton at the distance that you're measuring. How? And how did you build something with that level of accuracy and precision?
We actually built it with a lot of people developing technology, powerful lasers. We make the beams very big. When they get to the mirrors, we have the mirrors hanging in systems that don't let them move very much. We use them in detectors in the US and in other detectors, but a lot of people around the world developed these technologies.
Each arm of the L, you're saying, is 4 kilometers long. What does the light go through?
The light has to travel in vacuum, because if not, the air makes the trip not be completely straight. And we want the laser to be straight between the mirrors. That's the most expensive part of the system. But we did that, and actually we pumped down the air out of these beam tubes in the 90s, and we haven't opened them yet.
Are there other observatories now around the world that can look at gravitational waves like LIGO can?
There are, and that's very, very important. There is a detector taking data with us at this time in Europe. That's a Virgo detector, which is 3 kilometers long. And there's a detector in Japan that is also taking data with us. That's also 3 kilometers long, but it's inside a mountain, because if you're inside a mountain, the ground doesn't move as much. And it's very important to have more than two detectors, because you need to see the signal in more than one detector to be sure that it's an astrophysical signal and not something bumping into near the detector. But also, to know where the signal comes from, you need to triangulate. And triangulate means having at least three detectors, and four is even better. So that's why this is an international gravitational wave network.
But what has it shown us? And critically, what do we still want to know? What's the open question that perhaps we need to go beyond what the current generation of detectors can tell us?
Well, we have detected more than 300 signals now, even though the first one was only 10 years ago. And most of these signals have been collisions of black holes. So we are learning a lot about black holes, what kind of masses they have. They seem to prefer 10 solar masses, but they also seem to have another favorite spot around 30 solar masses. So this is something that astronomers are looking into understanding that. But we don't see those black holes very, very far away. So we want to build better detectors, longer detectors, so we can see those black holes at the time that the stars were first forming. And if there were primordial black holes before the stars formed, we would like to see those. For that, we need more sensitive detectors. But the other thing that we have seen only once so far is the merger of neutron stars, where we can see the light too. Neutron stars are the most compact of stars that can be formed by a supernova explosion. And neutron stars have atoms, and when they collide, those atoms collide and produce light, produce electromagnetic waves. So we can learn the nuclear physics of the stars with these signals. But they seem to be more rare than we thought. We have only seen two mergers of neutron stars and only one with light. And we want to see a lot more of those and in more detail so we can see what happens at the merger. So we are improving our detectors, but we want to be longer detectors too.
LIGO's Gabby Gonzalez on how we detect gravitational waves down here on Earth. Well, speaking of that, what comes next? Well, as we've been hearing, LIGO made history with the first detection of gravitational waves a decade ago, and since then, observatories like LIGO and Virgo and CAGRA have been catching ripple after ripple from across the cosmos. But the next chapter is even more ambitious, and scientists want to go big, really big. And the Laser Interferometer Space Antenna, or LISA, will become the first space-based gravitational wave observatory. It will do for gravitational waves what Hubble did for traditional astronomy. Ira Thorpe is NASA's LISA project scientist.
The emphasis on this anniversary that we're all celebrating is about a detection of a gravitational wave. But we want to do more than just detect them. We want to use them as a tool for doing astronomy. So just like we use light for doing astronomical investigations, we know we can use gravitational waves to do astronomy in a different kind of way. And one of the things going forward is just like we have different types of telescopes for looking at different types of light, we're going to need different types of gravitational wave detectors to access different frequencies or wavelengths. You could think of it as different colors of gravitational waves. The ones on the ground are limited to high frequency gravitational waves. And if we want to look at low frequency gravitational waves, we need to move our detectors to space, a little bit like the way we build things like the James Webb Space Telescope or high energy space telescopes in order to access parts of the spectrum that we can't see from ground.
So as the waves get bigger, so the detector needs to get bigger. It's a bit like in Jaws when they say you need a bigger boat, you need a bigger device
exactly.
in space. Yeah. So what have you got in mind then?
Right. So the simple explanation of LISA is take something like LIGO and scale it up by a factor of 1,000,000. Now, the LIGO detectors are a few kilometers in length, and if you do a little bit mental math, that means you need to be a few million kilometers, and you'll find out that a few million kilometers is more like the size of a star. And so obviously you're not going to fit that on a planet, even a small planet like Earth especially. And so that's the basic idea. We need to go to space. And so we just need a set of satellites, in our case, 3 satellites that form a triangle. And we shoot laser beams between these satellites and measure the distance between them. And as a gravitational wave comes by, it changes that distance and we can detect it on our spacecraft and then send that information back to Earth.
And how big are the displacements or the changes that you're measuring when these gravitational waves come through? How big is the signal that you're going to pick up with LISA?
Right. So obviously that depends upon how big of an event is producing these signals. But the term we use to measure how large a gravitational wave is, we call it strain. And this is a term we borrow from mechanical engineering or materials physics, which is a dimensionless way to measure strain, motion. So it's a change in length divided by the initial length. And so the way gravitational waves work is because they're changing space-time, if you measure between two parts that are farther away from one another initially, the amount of motion you get is proportionally larger, right? The larger you make that initial separation, the larger motion you get. And so because the LISA detector is a physical size is about 1,000,000 times larger than the ground-based detectors like LIGO and Virgo, the signals that we see are also about 1,000,000 times larger. So a million times larger turns out to be something in the order of picometers. So a picometer is a trillionth of a meter. So that's still not very large on human scales, but it's much, much larger than what the LIGO detectors are already capable of seeing on the ground.
We're down at the size of sort of atoms with that, aren't we? Almost. We're
Correct.
measuring
Correct.
this as though an atom is moving backwards and forwards. It's pretty amazing. How are you doing this? How are you detecting it with that level of accuracy and precision?
The kind of number to have in your head is, yes, we're measuring atoms scale displacements over a size of a star. In fact, it works out that you can just sit the sun inside that Lisa triangle would slip just inside the triangle made by these spacecraft. They're 2.5 million kilometers from one another. That's the length of the side of the triangle. So we use a technique which is similar to the technique that LIGO is using called laser interferometry. So interferometry just means we are going to use the wave nature of light as a ruler, as a way to make very precise distance measurements. The light that we use is in the near infrared. It has a wavelength of about a micron or a millionth of a meter. And so to measure a picometer, which is a trillionth of a meter, we need to measure that wavelength to a part in a million. Obviously, going that very, very, very long distance, even though we're using a laser, people think of a laser beam as going in a perfect straight line and never spreading out. Turns out physics doesn't work that way. Even with a laser, you get what's called diffraction. The beam spreads apart, and we actually lose most of the light in transmitting from one spacecraft to another. And so our main limitation is how much light we can get from one spacecraft across that 2.5 million kilometer distance to the other spacecraft.
What do you think you'll be able to see? If you can get this to work and get this flying, what is it going to reveal to us? What can we probe with it that we currently can't with Earth-based systems?
In terms of frequencies, LIGO is looking for things kind of in the audio band, almost in the same frequencies that we're hearing, maybe at the lower end of the audio band, things like hundreds of hertz type of frequencies. LISA is going to look at millihertz, or if you think about wave periods, it's things that are moving in the sort of hours time scale. And what you see there is there's two things. You can either see systems which are similar to the LIGO systems, so their masses are around the mass of the sun or a few times the mass of the sun. These are typically binary systems, so two things that are orbiting one another. But they're at a much earlier epoch in their evolution. So the way gravitational waves work, you get a pair of binary stars or black holes or neutron stars. They're orbiting one another. They're producing gravitational waves. Those gravitational waves carry energy away from the system, and so the objects fall towards one another. And it turns into this sort of runaway process where the closer they get, the more energy they radiate. So the faster they fall, so they get closer, so more energy is radiated, on and on and on until they crash into one another, and you get a big burst of gravitational waves and maybe a big explosion if they're made of something other than just pure gravity like a black hole. So we can see the same types of objects that LIGO sees, but much earlier in their evolution. They spend more time there, and so we can see a whole bunch of them. And the other thing we can see, which for many people, including myself, is maybe the most exciting, is we can see much, much bigger black holes. So the maximum frequency that the black holes get to is basically when they touch each other as they're orbiting. And the bigger black holes that you get, that frequency is lower. So rather than looking at black holes that maybe originated from the collapse of stars, which is what LIGO is likely seeing, LISA will look at mergers of black holes when you have galaxy mergers. So black holes that are millions of times the mass of our sun, like the one that we have in our own galaxy. And we know that galaxies merge to form bigger galaxies. And we also know that most galaxies host a black hole. And in fact, that black hole is actually proportional in size roughly to the size of the galaxy. And so we expect we will see mergers of these million, maybe even up to 100 million times the mass of our sun, black holes that are arising during galaxy mergers as the universe is being built up into the system we see today.
It's amazingly exciting, isn't it? But how long have I got to wait before I start to see this?
Well, so roughly a decade. So the European Space Agency is running the mission. Their launch date is 2035. So that's 10 years from now. And both the European Space Agency, all of the European member states that are contributing, and NASA that are contributing are working hard to make sure we meet that date.
Absolutely a date to look forward to. That was Ira Thorpe at NASA. With LISA on the horizon, it seems that we're about to hear the universe in ways that we never before thought possible. We truly are, as Isaac Newton famously said, about to stand on the shoulders of giants. Next week, we're going to be examining lung cancer. It is the world's deadliest cancer. It kills more people each year than breast, prostate and colon cancer put together. But are we getting any better at detecting and treating it? That's the question. Meanwhile, thanks very much to everyone who is helping us out here at The Naked Scientist with our running costs. If you'd like to chip in, we've made that very easy. Please do go to nakedscientist.com/donate. It really helps and we really appreciate it. And one other thing we really appreciate is if you could write us a review on the podcasting platform that you get this program from. That helps too. You can also follow us on LinkedIn, Instagram, and X, of course. The Naked Scientist is supported by Rolls-Royce. I'm Chris Smith, and from everyone here at the team, thank you for listening. A very big thank you to Alice Archer, physicist at Cambridge, and intern with us from Queen's College in Cambridge, who put the programme together. Thank you, Alice. It was brilliant. And until next time, everyone go well, and we'll see you soon. Goodbye.